Problem 66. The electric field for an electromagnetic wave is given as this. Find the angle of polarization of the electric field vector. Assume that we are on the origin, and so x equal to 0 and y equal to 0 here, and t equal to 0 as well. So let us see what the electric field vectors look like. So at the origin and at t equal to 0, Ex is given by 5 E naught and Ey is minus 7 E naught. So essentially this is 5 and this is minus 7. So we are here. So at t equal to 0, the electric field vector would look like this. The polarization angle theta is given by tan inverse of 7 by 5. We have to include a minus sign because we are in the fourth quadrant. So option C is the correct answer. Problem 67. A plane electromagnetic wave traveling in free space is incident normally on a medium of refractive index 1.6. What is the transitivity of the medium? So we know the transitivity is given by 4 n1 n2 divided by n1 plus n2 whole squared, where n1 and n2 are the refractive indices of the two mediums. So let us put that. So 4 into 1.6 into 1 divided by 2.6 whole squared. So let's simplify this. 4 into 1.6 divided by 2.6 times 2.6, and if you calculate that, this would be 160 divided by 169. So option D is the correct answer. Problem 68. Two magnetic dipoles of magnitude m each are placed in a plane as shown in the figure. The energy interaction is given by. So we recall two expressions. One is the magnetic field is given by mu naught m divided by 4 pi r cubed 2 cos theta r cap plus sin theta theta cap. This is the magnetic field produced by a magnetic dipole, and the energy of interaction is given by minus m dot b. From the figure we see that theta is 45 degree. So the magnetic field can be written as mu naught m divided by 4 pi d cube times 2 by root 2 r cap plus 1 by square root of 2 theta cap, and the direction would be, this would be the r direction and this would be the theta direction. The second magnetic dipole is pointed in this direction, so we could write the second magnetic dipole like 1 by square root of 2 r plus 1 by square root of 2 theta cap. So let us now take the dot product of m dot b, and this is equal to mu naught m by 4 pi d cube times 1 plus 1 by 2. So this is mu naught m by 8 pi d cube. So the interaction energy would be minus of this. So option C is the correct answer. Problem 69. An air-filled rectangular waveguide has dimension 6 cm by 4 cm. The cutoff frequency for TE1, 0 is, we know the cutoff frequency can be expressed as C by 2 pi square root of m pi by a whole squared plus n pi by b whole squared, where a and b are the dimensions of the rectangular waveguide and c is the speed of light. In this case we have to calculate the cutoff frequency corresponding to this. So we take m to be 1 and n to be 0. So if c, the cutoff frequency, is c by 2 pi times m, that is 1 pi by a. So this is c by 2a, which is equal to 3 times 10 to the power 8 divided by 2 times 0.06, and if you calculate that, this would be 2.5 gigahertz. So option A is the correct answer. Problem number 70. A certain state psi satisfies this. and this, where L is the angular momentum operator. What is the uncertainty of Lz in Z component? If we choose the basis to be the eigenstate of L square and Lx in this way, the state can now be written as 2, 2, because L square, the eigenvalue corresponding to it is L times L plus 1 h bar squared, and this is 6 h bar squared, so which means L is equal to 2, and Lx, the eigenvalue corresponding to this is m h bar, where, and this is equal to 2 h bar, so m is equal to 2. So the state is 2, 2. Now we could write L squared to be Lx squared plus Ly squared plus Lz squared, and due to the symmetry we could assume this to be same and equal to 2Lz squared. So the expectation value of L squared is equal to the expectation value of Lx squared plus 2 times the expectation value of Z squared. So we can now put this to be 6, this to be 4. So we can find Lz, the expectation value of Lz squared is equal to 6 minus 4 divided by 2 h bar squared, and that is h bar squared. Now Lz operator can be written as the latter operator L plus and L minus, but when this operators acts on these 2, 2 states, it increases the value of m, so the expectation value of Lz will be 0. So we find delta Lz is equal to square root of expectation values of Lz squared minus square of the expectation value of Lz, and this is square root of h bar squared, and that is h bar. So option A is the correct answer.